Thank you, Andrew. I consider this a considerable honour. Although I have been retired for 7 years, I consider myself out of date, but I even wondered when I started my presentation whether you're still using PowerPoint. And I found out you were, so bad luck. I think it's very appropriate that Andrew has asked me to talk on this theme of MacArthur beginnings to present, because MacArthur was a great man. And my talk is going to talk briefly about his history, a little bit less about what we have done since then, because I'm sure that'll be covered by other speakers who are looking at advances in fire behaviour research. And I will just ask a few questions at the end that have interested me as I sort of work through on fire behaviour. And one of these things will work, I think. Alan McArthur was brought up in Western New South Wales. He went to Yanco Agricultural College, joined the Forestry Commission of New South Wales as a plantation forester, and was appointed as the first fire control officer of the Hume Snowy Fire Prevention Scheme in 1951. He then, in 1953, moved to the Commonwealth Forestry and Timber Bureau to do research and was director of the Forest Research Institute in 1970. Alan was brought up on a wheat farm at Merriwagga in New South Wales. Merriwagga is halfway between Griffith and Ivanhoe, and it's about the western end of the wheat belt, and beyond that you're into Gaffer country. The experience that, firstly, Alan was homeschooled until he went to agricultural college, and his experiences being raised on a wheat farm gave him a very close familiarity with the problems of firefighting in the bush and the use of fire in the rural and agricultural community. The thing that changed Alan's career, I believe, was the Mangapwa fire in 1952, shortly after he was appointed as the fire control officer for the Snowy Mountains area. This fire started by fettlers burning off the railway verges. It was common practice in those times, and although the fire broke away, it was controlled by the local brigades at 150 hectares, and then 2 days later, under extreme conditions, burnt to the slopes of the Snowy Mountains area, 100 kilometres east, and burnt a few state forests that Alan was responsible for on the way. I think this convinced him that there was a need to properly rate fire danger, and to do that he would have to understand fire, and so he took up this position with the Commonwealth Forestry and Timber Bureau to do research into fire. His great friend was Harry Luke. They've had a lifelong association and friendship, and they worked together from the very early days, and it was an interesting association. Harry was the fire control officer of the New South Wales Forestry Commission, and he was very active in promulgating information and research about fire. And as soon as Alan would produce any sort of new table in a draft, Harry would get a draft form, he'd print it up on leaflets and distribute it to foresters in New South Wales before Alan, we often used before Alan got it published. Alan might have complained about this occasionally, but not too much, because later we find out he did much the same thing. They continued to work, and their association, of course, culminated in the production of Bushfires in Australia, which is still an outstanding text. Alan saw the problem in this way, that it was fire is a chaotic chemical reaction. You have great variation in the fuel bed, the terrain, and the weather elements, which vary in space and time, and that all these variables interact with each other. And they interact on scales that also vary depending on the intensity of the fire. And so, to attack this problem, his philosophy was that because there was no theoretical basis for fire spread, then he would have to do empirical research. Simply, as we say there, measure all the obvious variables. He correlated by graphical analysis, and he then related his in-forest measurements of the weather variables to the standard meteorological observations, because he was firmly of the proposal that he had to get any rating guide accepted by the Weather Bureau, and that would be a national forecasting tool. He set about, as Andrew said, these experimental fires with forestry students who were very willing workers, but unlike Andrew said, they weren't entirely free. I remember burning one in a survival tent once, and it cost me 2 cases of beer. Here we have experiments in Cowan around about 1956. The bloke is marking the head of the fire, albeit small, with cut sticks. The other blokes are marking the perimeter with rocks that they've picked up and written the time on in lumber crayon. The fires were quite brisk, and at this point I'll say there are very few photographs of Alan McArthur in the field, and that was mainly because he had the only camera. At the conclusion of the fire, then the forestry students had to put it out using hand tools, dry firefighting, and Alan would rate their degree of difficulty in doing this task and record this along each fire. And this rating was Alan's expert opinion of suppression difficulty, and this became the fire danger classes that you are familiar with in the forest fire danger meters. The end of the fire, the rocks and the sticks were surveyed. The students reconstructed the fire spread map, and that was the information for Alan's work. Similar work was done in Western Australia, and Western Australia had a burning off program underway. It was mostly constrained to burning 20 or 30 metre fire breaks, and occasional areas was in broad area. And because of this burning, that was a spot that Alan went to quite frequently and did research and got the data for his prescribed burning guide mostly from the fires in Western Australia. He made some assumptions, some of which were common at the time. One was that the fine fuels, less than 1/4 inch in diameter, were the fuel that dominated the propagation process. He assumed that fires reached a quasi-steady state depending on the fuel and weather. And although a lot of his fires were going through a build-up period, he would plot the build-up and then make an extrapolation and decide what the steady state would be for that particular fire. He assumed that the rate of spread was a function of wind velocity squared, and that was a firm conviction he had that remained for a long time and was really instrumental, the basis of his analysis that he did on mostly semi-logarithmic paper to account for curvilinear relations. And he was absolutely convinced that the rate of spread was directly proportional to the weight of fine fuel, or the weight of available fuel. The outcomes you're familiar with, the fire danger rating systems, he did similar work in grasslands. A lot of that was up in Queensland at the time of the Brigalow clearing. And in 1962 he produced his seminal work of prescribed burning in eucalypt forests, which set out the first prescribed burning guide. Another point that was critical in Alan's promulgation of fire research and fire information were the dwelling up fires of 1961. Alan firmly believed to try and go to as many wildfires as he could and photograph them, and it's not a bad philosophy that people that are unfamiliar with fires should perhaps carry out. The dwelling up fires burnt something like 146,000 hectares, mostly in the areas where a division of the West Australian and South West forests where prescribed burning was limited, and a reconstruction of those fires gave Alan a lot of the evidence he needed to promote his theories. He was involved in the Royal Commission, and the key recommendations that he probably wrote into the Commission report that you needed more research into fire and you needed to extend the control burning practice. One of the key photographs that was very influential and used a lot in the early 60s was this photograph, which was taken near Dwellingup, where a crown fire coming through 20-year-old fuel ran into a 2-year-old fuel and immediately dropped out of the crowns, because in those days there was a total conviction that if you had a crown fire, nothing would stop it until you ran out of trees. And so the concept of reducing the fuel under the forest to prevent crown fires was not widely accepted within the Forestry Commission until Alan McArthur promulgated it, and this photograph was instrumental in helping him. Alan lectured at the Australian Forestry School for quite a while, and so he had a very blunt and powerful manner. I can still remember him walking into the class for his first lecture and jangling his keys in his pocket and announcing, "Actually, I'm not a lecturer, but I'm here to teach you about fire." That blunt attitude, plus the use of the students during the summer fire exercises, which were in January mostly, in the middle of summer. Fires were real, the work was hard, and Alan's confidence in being able to light experimental fires in the middle of January with only a crew of students to put it out left a fairly lasting impression of those people who worked with him. There were also some other helpful attributes that Alan had. He was a gambler and a bridge player, and he was a very good gambler, as I found out to my expense more than once. He eschewed statistics. He considered statistics only got in the way of a good model, and if the data fell outside what he believed that his model would say, then he said there had to be another reason for it, which I don't know, and so I ignore it. He did maximise the data. Rather than going through the means, he tended to take the uppermost range of the data to use to establish the relationships, and so probably working for his data on probably the 95th percentile. Being with the Commonwealth Forestry and Timber Bureau, he also coordinated fire control activities for the states, and part of this coordination was pulling together an annual fire control officers conference, where a relatively small community of fire control officers in forestry were drawn together, discussing progress of how they went along, and a pretty good venue for him to indoctrinate them with the new work that he was doing on a regular basis. He, again, the Commonwealth Forestry in the 60s or late 50s and 60s had access to international travel, which was not readily available to people in the States. And so Alan travelled quite frequently to America to find out what they were doing, and brought back a lot of innovations, and which often were immediately taken in. One of them, for example, being the McLeod tool. When he saw that, he said, of course, that's a useful instrument, we've got to use it. He was a forceful and influential character, and he coordinated early events of international cooperation. He went with Harry Luke to the first UN fire study tour in the early 60s. That tour was held in the United States, and Alan said the United States is far too sophisticated for most of the countries attending this fire study tour, who are mostly developing countries. You would be much better off coming to Australia. And so he organised the second UN study tour in Australia in 1969. Since then, there's been a regular exchange, international exchange of fire control people between America and Australia. His work, or the students that he taught, were set out to look at fire research because Alan believed that his burning guide was particular to the particular dry forest that he was working, and so for the states to improve their burning guides, they should take his model of research and create burning guides in their particular forests. And they're just a few of the characters who continued Alan's work. Aerial prescribed burning was sort of given a big boost when David Packham from CSIRO developed the ignition, the incendiary, and the safe priming device for use in light aircraft. And by 1965, it was being introduced into Western Australia on a large scale. All of the burning guides followed this procedure, and being foresters, there was an objective straight away that if you were going to burn the forest, you had to do it with minimum damage to the forest trees that would later be harvested. And so the process he used in his guides, and everyone else pretty much followed, was to define the level of damage that you were prepared to accept, determine the fire characteristics that would give you that damage, determine the rate of spread and the burning time, and then set your ignition spacing so that individual fires would coalesce just as the weather conditions were becoming milder. This was good because the burning guides that were established were, as we find out later, burning mostly well below the potential burning rate for the conditions that they were carried out, because they were all still developing fires. But as they got to a significant size, the conditions were milder, and so you didn't get any great escalation of the behaviour. Aerial burning was introduced into the ACT in 1967 when we burnt the Flea Creek catchment. Didn't get burnt again until 2003. This burn was carried out in mountain country in Bemboka in 1968. Very successful burn. You can see under a strong inversion, and so the scorch level on that series was about 2 metres. Smoke constraints now will stop you using those conditions, unfortunately. Just want to talk a little bit briefly about the fire study tours. Because of Alan's international travel and his in character, these were important in introducing his idea or new ideas back into Australia and into research. Although he didn't have any time for laboratory studies, he would take anything from them that would appear useful. And one example was this of the relationship between the diameter and the packing ratio of the fuel. You could see a use for that. Another example was the Keach-Byram drought index tables, which Alan obtained a draft copy of these tables on one of these tours, decided that was very useful material, and several years before the US Forest Service published the tables, he'd already made a correlation between the build-up of fires and introduced it as a component part of his fire danger rating system. He also got involved in international cooperative studies. In 1967, this project Flambeau was a study of mass fire behaviour at a place called Bishop Pass. It was financed by the Office of Civil Defence in the US and primarily based on a theory of that a nuclear weapon detonated at a kilometre above the ground and igniting the fuels below it would cause more damage by induced wind flow than it would if it was detonated at ground level. Alan had no photos because shortly after this photo, it snowed the next day, the burns were cancelled, and Alan in his brash way says, well, you know, you really can't burn in this place at 8,000 feet. You've got to come to a place where fuels will actually burn, so you better come to Australia. And so he organised the US Office of Civil Defence, the British Office of Civil Defence, and the Australian Defence Department to finance the final burn of this mass fire project in Australia, and instrumented by the US Forest Service for the instruments they were using at Flambeau. The experiment was carried out at Emerald as at that stage the Brigalow Clearing Project meant there were large areas being of brigalow, which is an acacia, and a very hard timber, on very fertile black soil plains. So it's all been cleared for grasslands, for pasture. And there was a lot of heat fuel, and we said, well, this is excellent. We can put together your fuel load that you postulate will be in San Jose, which was one of the key things. We'll ignite it instantaneously and we'll burn it under much more dangerous conditions. Unfortunately for us, we got 2 inches of rain 2 days before the burn was due to go. And even despite the high temperatures at the time, the Defence Department's program that things had to be done on schedule meant that we could only get 1 day's delay. And so we sent the burn off under somewhat less than optimal conditions. But on the other hand, because brigalow is so dense and burnt extremely cleanly, this whole fire went off without any smoke. And for the first time we got the opportunity on these mass fire studies to see what the flames were doing, which curiously was not very much, even though there were vortices and loud bangs and stuff being thrown around, winds being introduced. Everything was much as normal. You can ask me later whether anything came out of this project and I'll give you an answer. The influence of the advances since MacArthur. The major advance, in my opinion, was the relationship of head fire width to rate of spread, and the presence of quasi-steady states of rate of spread at various stages of the fire, which are below the potential rate of spread. When you started working with the potential rate of spread, you found that the relationship between spread and wind speed was a linear relationship, or slightly negative exponential, maybe. We have looked at the influence of fuel structure on rate of spread, and that's a major advance. I think Jim's going to enlarge on later. The behaviour of firebrands introduced in spotting. I don't know whether Peter, I think someone's talking for Peter on that. Since MacArthur, we continued with this program of experimental fires, varying intensity from the very low fires used for prescribed burning to pretty reasonable reproductions of high intensity forest fires, while still only about 1/10 of the maximum potential. It covers probably 95% of fires that occur. I'll just talk briefly about this fire. It was part of the experiments that led to finding out about the effect of head fire width. It's burning in annual sorghums, or annually burnt sorghums, up in the Northern Territory. We used essentially the same techniques as MacArthur, except instead of rocks we had big pieces of tin bent over that we could find in the bush. These fires were large. They travelled at up to 6 kilometres an hour, and they were marked every minute. And at 6 kilometres an hour, if you're a slow jogging pace, unless you've got to stop every minute and write something down on a piece of paper, in which case you're doing a fair gallop by the time you come out the other side of the block. On the bigger fires, for safety, we could get inside the fire and mark them from the inside, and then the fires could be burnt out safely without catching someone between. And you can only do it on this type of fire, really, because it's annually burnt, and it's an area endemic with termites, and so there is no residual fuel on the ground. And we found that the best place to walk was about 20 metres behind the head fire, because there you've got clean air coming down into the fire. I ignored MacArthur's advice and tried to analyse this data statistically, and could prove conclusively that fire spread was independent of the wind speed. I then took heed of MacArthur's advice and put the stuff away for 10 years till I found out what was causing the problem. Our finding came largely by serendipity, because we were lighting fires which were supposed to be 100-metre fires in length for a series of revisions of the grassland series, and because of switches in wind direction, the ignition length was not always the same. And so we found that the rate of spread was dependent on the ignition length initially. On further examination, we concluded that the rate of spread was actually dependent on the head fire width, which was the part of the flames which are leaning over the fuel in front of it. It was sort of somewhat indefinite definition, but the best we could come up with. And in this case, the fire in the middle, which was from a 50-metre ignition, has narrowed to a point and is now travelling slower than the first fire up above it. This explained the process that was going in those very large fires that we carried out, and brought away the concept of quasi-city-state rates of spread that were dependent on the width of the head fire. For your future research, I just have a few areas of concern that I think you should think about. Our suppression capacity is puny compared to the range of potential fire intensity. Let's say about 2 to 2.5% of what intensities you can expect. And I think that this has to be kept in mind, because obviously bigger and better suppression techniques are not working, as you can see in the US. We're still killing people. Again, the Yarnell fire disaster is an example. Not necessarily related to fire behaviour perhaps, but we're still killing our own people as well. We have increasing restrictions on prescribed fire, mostly now being brought about by the incursion of urban city dwellers into the bush environment, with little knowledge of what is required for fire protection, but also forming an impossible boundary for people who have land around that are trying to reduce. It may mean that we need to be better and more precise with any burning guides that are produced. There's a failure to fully implement the existing burning guides, with the notable exception of Western Australia. And John Marsden Smedley may bring you up to date later with what's been happening in Tassie. There are unexplained outliers in our existing data that, despite all efforts, we could not explain, and sometimes we had fires that were twice the amount of what our mean analysis told us. And there are incidents of intense fire behaviour in other wildfires which are not easily explained either. I have some questions, and I'm going to tell you what to do at my stage in life. But I'll ask you, what are the key elements critical to fire spread? Can we better define and measure the fuel structure? And how does fire interact with the atmosphere and topography? And just to finish off, we'll just look at a few examples. These are two simultaneous grass fires, both travelling under the same conditions of wind and fuel moisture at 3 kilometres an hour. The top one is in half the fuel load, in half the fuel height, and has 1/6 of the flame height of the fire below it. Now, obviously, if radiation is your primarily heat transferring mechanism, it doesn't apply in these fires. So what is the critical process going on right at the front of those fires where causing it to travel at the same rate? An example from Black Spruce woodland in Canada, courtesy of Brian Stocks, and experiments they were doing here. Black spruce forms a coppice clump and has lichen in between it. When the fires start off, obviously the spruce crown's out and the flame heights and the lichen are in centimetres. However, as the fire builds up, eventually the fire integrates the difference in the fuel and forms the normal parabolic head that you would find in almost any fire burning through a continuous fuel type. I see there are questions for us in terms of our stringy bark forests and their behaviour, especially close to areas of urban. Is there potential to take out one of the fuel elements? If we understand how this integration process goes on, we might be able to sort that question out. And finally, some interaction of the fire and atmosphere, which is just an example from Project NARIC, which we carried out with Western Australian Forest Department in 1983. This is a shot taken at about 40 to 45 minutes after ignition and relates to the next slides that you'll see. I just point out that there does appear to be a downdraft in that photo coming into the back of the fire, and that model was very similar to the results that came out of some of the Flambeau fires, that there appeared in those mass fires to be a jet stream which came down into the back of the fires and then was carried up in the convection column. At 40 minutes for ignition, again about the same time as that photo, you can see these fires on the perimeter. Hang on, whoops, sorry. Go back. This one. Are being drawn towards the head of the fire, and the fire's convection is blocking the influence downwind. 7 minutes later, as coalescence occurs, you can see that despite the distortion of the imagery, the fire has formed a wide head as the spot fires ahead of it have been drawn in towards the centre. And this, I believe, is a process critical to the acceleration of fires, the roles that spot fires play in accelerating a fire. It's not, as being proposed by many, the coalescence downwind. It's rather increasing the head fire width. Most of you have probably seen this, but because this is probably my last public talk, I'm going to play it anyway because I like it. Let's see if this works. Richard, start it up. Good on you. Great friend and very useful person to me as I age, this young Richard. The wind is blowing directly away from the camera side as you're looking at it. It's in Jarrah Forest in southern Western Australia, the southern districts. Has an intermittent blader. This is 16-year-old fuels, an intermittent blader of shrubs, and the spot fires falling down in front, as you noticed in the previous slide, are actually in an area of variable wind, and not being blown completely. I want you to now note the time of the tall flames. That was about 10 seconds. And the material burnt in 10 seconds is material less than 2.5 millimetres. So here we're in the downdraft phase of the fire, which is flattening the flames of the residual burning fuel. And so most of the fuel load of 80% or 80% of the fuel load is burnt by these surface flames burning down into the fuel bed. And someone may be able to explain to me, after seeing this, why Byram's fire intensity equation ever works at all. Well, I've used it myself. What do we do now, Richard? You have to come and help me again.
Go to the next slide.
Go to the next slide. Oh, it does work. No, it stops.
Yeah, there's a trick.
Obviously, there's an advance in machines for PowerPoint. I'll leave you a warning from Gaston Bachelard, a French psychologist who looked into fires in the 1930s, that the initial charm of the object is so strong it will warp the mind of the clearest thinker. Just think about that. And finally, my only piece of advice that I'm going to offer this community: keep your eye on the ball and make sure you follow through. Thank you.